Imagine you were driving a digital car in like a really high-end video game.
Oh, yeah, like at 100 miles an hour.
Exactly. You're flying down the track,
Yeah.
and then you suddenly take your finger off the gas.
Right, the car slows down.
It slows down, and you can literally feel that virtual wind resistance pushing back, that gradual deceleration.
It feels incredibly real.
It really does.
Yeah.
But it makes you wonder, how does the game actually know exactly how fast to slow you down at any given microsecond? Like, how does it make it feel that realistic?
Well, to answer that, we aren't actually looking at a textbook on game design today.
No, we are not. Instead, we are decoding this dense but honestly fascinating set of materials covering first-order ordinary differential equations.
Which, I know, sounds like quite a pivot from video games.
It really does.
But it really isn't. Because it turns out the math making that digital car feel real is, well, it's the exact same math keeping cloud servers from crashing during a traffic surge.
Wait, really?
Yeah, and the exact same math keeping a rocket from falling out of the sky.
That is just wild to me. Usually when you hear the words ordinary differential equations, there's this visceral reaction.
Total panic.
Right. You picture a dusty chalkboard covered in incomprehensible Greek symbols. You start sweating a little.
Your brain just preemptively prepares for total information overload.
Exactly. But I want to reassure you, the listener, this is not an audio textbook. Our mission for today's deep dive is to show how everything in the universe that changes speaks this exact same, surprisingly simple mathematical language.
It really is the ultimate universal translator for dynamic systems.
I like that. Universal translator.
Yeah, because if something is moving, shrinking, growing, or, changing over time, differential equations provide the structural blueprint of that change.
So it's like the math of time passing.
Essentially, yes. It is how we quantify the very concept of now turning into later.
Okay, let's unpack this, because this is the ultimate aha topic for a curious mind.
I completely agree.
But before we can explore how these equations basically build modern technology, we need to understand the structural logic of what they actually are. So what exactly is an ordinary differential equation, or ODE?
Well, at its fundamental core, an ODE is just a mathematical relationship that ties a specific function to its derivatives.
And a derivative is simply a rate of change, right?
Exactly. Think about driving a physical car on a real highway.
Okay, I'm picturing it.
Your position on that highway is the function, your speed. So how fast your position is changing is the first derivative.
Got it. Position and speed.
Right. An ODE takes those pieces, the current state of a system and how fast that state is changing, and it binds them together into a single mathematical sentence.
Hold on, I'm following the car analogy, but if the material we are diving into specifically focuses on first-order, first-degree ODEs.
Which it does, yeah.
That means we're only looking at the first derivative, right?
Oh.
Speed.
Right.
So aren't we ignoring acceleration entirely? Doesn't that make the model totally inaccurate for the real world?
That is a very fair question. But it actually highlights why first-order equations are so vital.
How so?
Well, yes, first order means we are dealing strictly with the first derivative. The change in y over the change in x, or di over dx.
Right, no acceleration.
We aren't calculating acceleration, which is the second derivative. But in the real world, countless physical systems don't actually have acceleration in the way a car does.
Wait, they don't?
No, their rate of change is driven entirely by their current state. Think about a cup of hot coffee cooling down on a desk.
Okay.
The rate at which it loses heat is dictated solely by how hot it currently is compared to the room. There is no heat acceleration.
Oh, wow. I never thought about it like that.
Right. That is a pure first-order dynamic system. And first degree just means that the derivative isn't squared or cubed. It is the most foundational building block of dynamic math.
So we have an equation describing a fundamental rate of change. But simply writing down the equation isn't the same as actually finding a solution.
No, definitely not.
When you need to isolate the answer, how do you mathematically untangle it? The first method laid out in the materials is called the variable separable structure.
Yes, the classic starting point.
The best way I can visualize this is that it feels exactly like sorting laundry.
Sorting laundry. Okay, I'm intrigued.
Yeah, you've got this mixed up basket of x terms and y terms all mashed together in the equation. And the goal is to factor it so that you put all your darks, let's call them the x variables, and the dx on one side of the equal sign.
And all your lights, the y variables, and the diode on the other side.
Exactly.
That analogy actually captures the structural elegance perfectly. You cannot easily integrate or solve an equation if the variables are all tangled up.
Right, they have to be separated.
Yeah, by pushing the x terms to one side and the y terms to the other, you create a scenario where you can perform integration on both sides independently.
It's clean.
It's clean, it's highly logical, and it yields what we call a general solution.
But, laundry isn't always that easy. What happens when the colors bleed?
Ah, yes, the messy equations.
This brings us to the second method, the homogeneous structure. Sometimes you have a function where the x and y terms just cannot be cleanly separated,
Right, they are algebraically fused together.
but they share identical total degrees in every single term. When that happens, there is a suggested substitution, replacing y with v times x.
Which changes the derivative die over dx into v plus x times dv over dx.
Right, and I just have to ask, is this substitution essentially a mathematical cheat code?
What do you mean?
I mean, are we just tricking an unsolvable equation into becoming a simple laundry sorting problem?
What's fascinating here is that, yes, it is absolutely a mathematical cheat code, and it works brilliantly.
I knew it.
Yeah, when the terms are too entangled to separate, you introduce this new variable, v, which just represents the ratio of y to x.
Okay, but how does that actually untangle them?
Well, here is why it works. Because every single term in the original equation has the exact same total degree. Let's say they are all squared. When you substitute v times x in place of y, every single term now contains an x squared.
Oh, I see where this is going. Because they all share that x squared now.
Exactly. You can literally just factor the x squared out of the entire equation and divide it away.
It just vanishes.
It vanishes. The knot tying the variables together simply dissolves. The messy inseparable equation is mathematically transformed into a variable separable one.
That is so clever.
The cheat code works. You do the substitution, you easily integrate it, and then you just swap the y and x back in at the end.
I have to admit, mathematically, that is incredibly satisfying.
Yeah.
But there is a massive catch to all of this integration, isn't there?
There's always a catch.
When we do this, whether it's separated easily or through our cheat code, we don't actually get one single definitive answer. We get a general solution that includes an arbitrary constant.
Right. Always represented by a capital C.
Meaning, the math gives us a family of curves, infinite possibilities.
Right, because integration tells you the general shape of the curve, but it doesn't tell you exactly where it sits on a physical graph.
How do you find that out?
To figure that out, to really nail the curve down, we need boundary constraints.
Which anchors this floating theoretical math into hard reality.
Precisely. A boundary constraint is a known, indisputable fact about your specific physical scenario.
Like what? Give me an example.
For example, you might know that at time 0, a chemical reaction starts with exactly 5 grams of material. So at T equals 0, Y equals 5.
Oh, I get it.
Yeah, and when you plug those known values into your general solution, you can finally solve for that mysterious constant C.
And suddenly, that infinite family of curves collapses into a single particular solution.
Exactly. One that perfectly models your exact physical reality.
So we've essentially built a mathematical cage that traps this infinite concept into a single reality.
That's a great way to put it.
But let's take this off the chalkboard. If I'm an aerospace engineer building an actual physical altimeter, how does capturing this particular solution keep a plane from crashing?
This is where the theory becomes incredibly tangible. In aerospace engineering, modeling atmospheric pressure is literally a matter of life and death.
I would imagine so.
The rate at which atmospheric pressure decreases as you climb in altitude is actually proportional to the pressure itself.
Let me visualize that. Meaning, the higher you go, the less air there is to begin with.
Right.
So the rate at which the pressure drops actually slows down the higher you climb.
Yes, exactly. Mathematically, it's a classic variable separable ODE, dP over dH equals negative K times P.
The change in pressure over the change in height equals a negative constant times the current pressure.
You got it. And when you solve that ODE, you always get an exponential decay function. Understanding that specific curve is absolutely critical.
Because if you get it wrong,
If you don't model that exponential decay perfectly, using the right boundary constraints, like, the air pressure at sea level on that specific day, your altimeters will give false readings.
and your aircraft cabin won't pressurize correctly. It
Exactly.
reminds me of a leaking bucket.
A leaking bucket.
Yeah, if you have a bucket full of water with a hole in the bottom, when the bucket is full, the water pressure is really heavy, so it leaks incredibly fast.
Oh, I see.
But as the water level drops, there's less water pushing down, so the leaking slows down. The less water inside, the slower it leaks. That's exponential decay.
That is a flawless physical visualization of dp over dh equals negative kst. The rate of change is entirely dependent on the current state.
But aerospace isn't just about passively floating in the atmosphere. It's about blasting aggressively through it.
That's very true.
What about rockets? The Tsiolkovsky rocket equation comes into play here in the sources, but why do we need differential equations for a rocket? Can't we just use basic high school physics? Force equals mass times acceleration.
Basic physics completely fails a rocket because a rocket is uniquely bizarre.
Bizarre how?
Well, to move forward, it has to aggressively throw parts of itself, specifically ignited fuel backward.
Right, the exhaust.
Yeah. So a rocket's mass is literally vanishing second by second as it burns fuel.
Oh, wow. I hadn't thought of it like that.
Because its mass is constantly dropping, the force required to accelerate it is also changing every single millisecond.
So a static equation just can't keep up.
No, a static equation cannot handle a mass that changes while the object is moving. That continuous chaotic relationship between velocity, mass, and time can only be formulated and solved as a continuous first-order ODE.
Okay, so we have airplanes and rockets, massive, roaring physical scale. I want to pivot entirely to electronics engineering, which is microscopic scale.
Oh, let's do it.
Let's talk about RC circuit transients. What happens when a tiny capacitor discharges electricity through a resistor on a circuit board?
Believe it or not, it's your leaking bucket again.
Really?
Yeah, in an RC circuit, when a capacitor discharges, the voltage drops. But the speed at which it drops is proportional to the remaining voltage in the capacitor.
Just like the water in the bucket.
Exactly. The governing first-order ODE here states that the change in voltage over time plus 1 over the resistance times capacitance multiplied by the voltage equals 0.
I'm going to push back here because this sounds almost too perfectly aligned.
I know it does.
Are you telling me that the math that keeps an airplane cabin pressurized at 30,000 feet is the exact same structural math that dictates how a microscopic timing circuit works in my digital watch?
It is the exact same structural language. Both systems mathematically yield an exponential decay curve.
That is insane.
For the discharging capacitor, the solution is V of t equals V sub 0 times e to the negative t over RC.
Okay, that's a lot of letters.
Basically, the physical resistance and capacitance on that silicon chip act just like the size of the hole in your leaking bucket.
Ah, I get it now.
This single principle dictates how long a signal takes to filter through a circuit board. The universe simply does not care if it is air molecules in the stratosphere or electrons on a silicon chip.
The mathematical rule of rate of change proportional to current state applies equally to both.
Exactly.
That is genuinely wild to think about.
And it actually gets better because electronics also rely heavily on that second structural method we discussed.
The homogeneous one.
Yes. Okay, I might get a little too excited about this, but you have to understand how beautiful this specific application is.
Lay it on me.
Think about inductor energization, RL circuits. When you look at how current builds up inside an inductor to create a magnetic field, it follows a first-order homogeneous structure.
Okay.
This specific math determines exactly how quickly electric motors or solenoids activate.
Look, when you flip a heavy switch.
Yes. When you press a button on a control panel and you hear that loud, satisfying physical snap of mechanical relay shutting.
I love that sound.
Right. The actual physical speed of that magnetic action is governed by a homogeneous ODE. The math dictates the physical snap.
That is incredible. Okay, so we've established how these equations govern the physical world.
Mm-hmm.
Mechanics, aerospace, electronics. Here's where it gets really interesting.
Oh, I know where you're going with this.
Because if you want to build a virtual world or manage abstract digital infrastructure, you cannot escape these equations. You have to use the exact same mathematical rules.
Right, because if a virtual world doesn't follow the mathematical rules of our physical world, our human brains immediately recognize it as fake or floaty.
It just feels wrong.
Exactly. And this is the entire foundation of physics engines in game development. Let's go back to your digital car from the beginning.
Yeah, taking my finger off the gas.
When you simulate that aerodynamic drag, the deceleration is proportional to its velocity. The faster the digital car goes, the harder the digital wind pushes back.
So just to be crystal clear, when I am playing a racing game on my couch, my console isn't just playing a pre-rendered animation of a car slowing down.
No, definitely not.
It is literally solving a continuous first-order differential equation frame by frame while I hold the controller.
Yes, it is. The game engine is constantly evaluating the rate of change. But here is the trick.
There's always a trick.
A computer operates in discrete, robotic steps, frames per second. It can't do smooth, continuous integration the way we would by drawing a curve on a chalkboard.
Oh, right, because it's digital, not analog.
Exactly. Instead, it uses numerical integration methods.
And this is where methods like Euler or Runge-Kutta come in from the source materials. But how do those actually work to fake a continuous reality?
Think about the Euler method first. Let's say your game is running at 60 frames per second.
Okay, pretty standard.
The computer calculates the exact slope of the curve, the rate of change, for that specific millisecond.
Got it.
And it uses that slope to blindly predict where the car will be 1/60th of a second later. It moves the car there, then instantly recalculates a brand new slope based on the new speed.
So it is taking tiny, rapid, microscopic straight lines to approximate a curve.
Yes.
But wait, if it's blindly stepping forward based on the starting slope, doesn't it drift off the true curve eventually? Like, if the curve is bending but the computer takes a straight step, it's going to end up slightly in the wrong spot.
Exactly. That is called numerical drift. Euler is fast, but it gets sloppy.
So how do they fix it?
That is why high-end physics engines use the Runge-Kutta method. Instead of just looking at the slope at the start of the frame and taking a blind step, Runge-Kutta calculates the slope at the beginning of the step,
Okay.
takes a test step to the middle, calculates the slope there, and then checks the slope at the end.
Oh, wow.
It mathematically averages all those slopes together before actually moving the car. It is far more computationally heavy, but it prevents the digital physics from drifting into inaccuracy.
So your gaming console is effectively doing complex calculus, averaging thousands of times a minute, just to make letting off the gas pedal feel realistic.
That's exactly what it's doing.
Faking continuous reality by taking highly calculated, microscopic digital steps.
I love that. And this same predictive math scales up to the internet itself, right? Specifically regarding queuing theory and cloud software engineering.
If we connect this to the bigger picture, this is arguably the most crucial application for modern digital infrastructure.
Really, the most crucial. Yeah, think about a massive cloud server during a major global event, like a highly anticipated streaming premiere or a massive holiday sale.
Everyone logging on at once.
Right. Web traffic doesn't arrive in a smooth, linear fashion. It arrives in chaotic surges. The server has a queue of tasks.
Okay.
The rate of change in that queue length, so how fast it is growing versus how fast the servers can process the requests, can be perfectly modeled using first-order rate equations.
Let me guess. The cloud platform uses an ODE to watch the rate of change in real time.
You got it.
And if the server queue is growing at a rate that mathematically predicts a catastrophic bottleneck, the system uses that slope to trigger an auto-scaling algorithm.
Yes.
It literally spins up backup servers before the crash ever actually happens.
Precisely. The exact same foundational math that calculates wind drag on a digital car is dynamically calculating server loads to keep the entire modern internet from collapsing under heavy traffic.
Okay, we have covered a staggering amount of ground, exploring these profound applications across both the physical and digital universes.
We really have.
We've gone from high-altitude altimeters to snapping solenoids and from video game physics to auto-scaling cloud servers. But we have to talk about execution.
Okay, let's talk execution.
Because, let's be honest, engineers at major tech or aerospace companies aren't sitting at wooden desks solving homogeneous substitutions by hand on a whiteboard all day.
No, definitely not. That would take forever.
How is this actually implemented in the modern workforce?
The modern toolkit relies entirely on code. Specifically, engineers use optimized standalone Python scripts.
The materials heavily highlight a specific tool inside the Python ecosystem called SIMPy, right?
Yes.
Standing for Symbolic Python.
Correct. SIMPy has a dedicated mathematical toolbox called zsolve. Engineers run this function directly inside a Jupyter Notebook environment.
And why Jupyter Notebooks specifically?
Well, they are incredibly powerful because they allow an engineer to mix executable code blocks, explanatory text, and visual interactive graphs all within a single document.
So what does this actually mean for the day-to-day job of a modern engineer? Because if a SIMPy Python script is doing all the heavy lifting of the actual integration, doing the Euler or Runge-Kutta stepping instantly, is the real engineering skill nowadays less about doing manual calculus and entirely about knowing how to properly set up the boundary constraints?
You've completely nailed it. The manual calculus is no longer the bottleneck of innovation.
That's wild.
Yes, you must understand the conceptual difference between a separable and a homogeneous equation. But the Python tool handles the actual integration instantly.
So the human element is something else.
The true skill of a modern engineer is defining the physical parameters of reality. It's knowing exactly what that boundary constraint is.
Remember that constant of integration, C.
Exactly, that family of infinite floating curves. The engineer's code acts as the bridge between that theoretical infinite and the practical, physical specifics of the machine they are building.
Because the computer is blind. It needs the engineer to tell it which specific curve to draw out of the infinite possibilities.
Exactly. And the true beauty of using mathematical simulators in a Jupyter notebook is the visual feedback.
Right, because you can see it.
An engineer doesn't just crunch cold numbers. They can dynamically visualize the system. They can tweak a boundary condition in the code, say, slightly change the starting server load, or alter the initial temperature of a component, and instantly watch the exponential decay curve physically shift on their screen.
That is so cool.
It empowers engineers to intuitively understand and play with the dynamic system they are building, rather than just getting bogged down and lost in the algebra.
It makes the math a tool for actual exploration, rather than just a massive academic hurdle to jump over.
Exactly.
We have journeyed through a massive amount of knowledge today. We started with the raw structural logic of an ODE, breaking down how variable separable equations require untangling and how homogeneous equations use a brilliant degree-canceling cheat code to force a clean solution.
And we saw how those theoretical structures are forcibly locked into physical reality by applying boundary constraints.
Right. And from that mathematical cage, we looked at how those solutions dictate the physical realities of altimeters reading atmospheric decay, rockets losing mass in real time, and the exact timing of discharging capacitors in our devices.
It's everywhere.
Then we took it into the digital architecture, seeing how video games use Runge-Kutta averaging to simulate continuous physics without drifting, and how cloud servers use weight equations to dynamically scale under massive pressure.
Right.
And finally, we brought it back down to the desk of the modern engineer, where Python and SymPy turn these abstract mathematical concepts into executable visual tools.
It truly is a profound realization that the mathematical language of change is completely universal across all these domains.
It really is.
So the next time you board a pressurized flight, or play a physics-heavy video game, or watch a cloud streaming service smoothly handle millions of viewers, take a moment to realize what you were really interacting with. You were watching first-order ODEs hard at work in the background.
It fundamentally changes how you look at the moving parts of the world around you. But before we wrap up, I want to leave you with one final thought to mull over.
Okay.
We've seen that everything from the air pressure in our atmosphere to the digital traffic on our internet servers follows these highly predictable, elegant rules of rate of change.
Yes.
It makes you wonder about us. Is there a complex first-order differential equation that could accurately model the rate of change in our own human habits or sweeping societal trends?
Oh, wow.
And if there is a math equation that perfectly predicts human behavior, what exactly would be our boundary constraints?
Now that raises a deeply fascinating question about free will versus predictable dynamics. I suppose we will leave that for you to ponder.
Thanks for joining us on this deep dive. We'll see you next time.